Professor Misra and Professor Dixit. And good afternoon, good morning, and good evening maybe, and namaste to all. So, as mentioned by Professor Misra and Dixit, I will talk about my career and how I can contribute to the IDRiM later on. But before this, I will try to discuss what exactly I am going to talk today. So today, basically, I'm trying to present, trying to link the early warning system with the Melamchi disaster that has happened in year 2021. And I'll try to link how early warning system or what could be the early warning system in future in its lesson learned from the Melamchi disaster. And at this presentation, I'll try to explain what exactly happened in the Melamchi, the prospects of Melamchi disaster, and then the existing disaster-related infrastructure in that area. And after that, I will try to explain the possibility of that kind of disaster in similar watershed. And finally, I will try to explain the mechanism of disaster that can be happened in South Asian Himalayas and way forward for early warning system based on the lesson learned from the Melamchi disaster. Exactly, I'm not the early warning system expert. My major is hydrology and hydraulics, basically modeling. And from the lesson learned from the different research with colleagues, I'll try to explain a few of my experience. We know Nepal's Himalaya are prone to disaster. And then due to the fragile and complex geological setting, physical diversity, topographical variation, climatic variation, and in addition to this, anthropogenic activities like haphazard land use planning, and then those kind of dozero activities, that means the unplanned road networks, aggravated the landslide, avalanche, debris flow, flash flood, droughts in higher Himalayas. So if you look at the global scenario, Nepal ranks on 11th in terms of vulnerability for earthquakes and 13th in terms of flood risks. So if you look at the recent statistics, Nepal is affected by multiple hazards. We can see most of the hazards are triggered by rainfall and leading to the landslide and flooding. If you look at the Melamchi flood 2021, we get 17 casualties, 23 missing, nearly 100 plus houses destroyed, several critical infrastructure destroyed. You can see from this figure also. So after next day of the Melamchi disaster, we visited the disaster-prone area, and we got that the around 50-meter bed rise of the Melamchi area. We can see from those photographs that most of the critical infrastructures building were damaged. You can see from those are the lifeline structures that has been damaged due to the Melamchi disaster. These are few glimpses, few pictures. We can see road networks, suspension bridge, bridges that has been collapsed. I'll try to show.
I am sorry, Mr. Thapa. May I request Alina Madam to put up the slides? I can't see the slides which Mr. Thapa has prepared. The slides which he sent to Madam Una today.
Today morning, yeah, this is the same slide.
Yeah, but I can't see those slides on the screen.
So I see it well and good. How about others?
I am also seeing it is good.
So I think it is better when you present, the slides should come up on the screen so that everybody can see.
Professor Misra, it is on the screen.
Yeah, it's on the screen. Me too. I can see here.
Screen.
Right.
Yeah,
I can't see it.
It's visible for me.
What about
see it?
What about
Brazil? Yes, I can see here. Melanchi disaster, various process leading
Yeah, it is, I mean,
It's
what?
displayed.
Somehow I don't see it here.
Pankaj,
Anyway.
Dr. Pankaj Kumar, do you see it?
Okay.
I can see the
Okay,
slides
all right.
also.
Okay, what
Okay,
about
sorry, Mr. Thapa,
Subramanian,
please
sir?
continue. Please continue.
Okay,
Yes,
okay,
Professor,
thank you.
I can see.
Thank you, Professor Misra. So if you look
Thank
at
you.
this figure, I'll try to explain what exactly happened in the Melamchi. I will try to explain the process. So in this slide, I just want to summarize what exactly happened in Melamchi. From this figure, you can see from the office stream, we can see the Melamchi disaster cannot be attributed to a single event. You can see lots of events in the figure also. The analysis by our team, that means the Nepal Engineers Association team, the World Bank, ADB, ECMOD, and different researchers, several researchers did analysis for the Melamchi disaster. And most of them suggested that the disaster was a result of multiple factors and processes that occurred at various locations along the Melamchi River. You can see from the figure also, I'll try to explain. Those figures explain the overview. So if you look at those things, you can see in the top earthquake activities in 2015, which induces small landslides. And also another triggering factor is the weather condition. That means the heavy snowfall and precipitation and sharp rise in temperature. Processes in the high altitude glacial environment, that means movement of glacier. Erosion of old landslide, you can see in these places, the landslide dam outburst flood from the old landslide. Erosion of old landslide and Memathan area, this is and then the new landslide formation is Melamchi Gang area, that means the Melamchi Gaon. River damming at the downstream area and sediment deposition, river bank erosion, that kind of processes you can see from the Melamchi disaster. So several studies summarize those disasters like this. That means you can see that those kind of hazards, both alone and in combination, single event and the combination of several events with other amplified the scale of disaster in downstream area. So if you just summarize, that means from the analysis, we can see that the no cloud burst event at that area, earthquake-induced landslides, small landslides, landslide damming outburst flood, bank cutting and degradation, and several lifeline structures had been damaged. So if you look at this two figure in 2010 and 2021, in between the decades, you can see lots of land use change. If this type of land use change need to be happen, are we expecting those? Are those type of land use plan is appropriate or not? We need to think. So those are still questionable for us. So if you look at the data, we can see that the left figure shows that in around 2 hours, there is blockage of the river from the data from the left figure also we can see. But there is no any early warning system, so people did not get any information of those blockages. But from the informal dissemination of information from upstream to downstream, saved several lives and the property. So if you look at the right side also, we can see several those kind of small landslide and those things, but we don't have information on those prior to disasters. So we need to develop some kind of early warning system. So if you look at these hydrometeorological stations in Nepal, we can see the sparse distribution of hydrometeorological network. If you look at the Melamchi area, we can find that the 6 meteorological stations, only 1 hydrological stations. We can see 1 hydrological stations at Nakot area, which I have shown before, the one graph. And then the 2 meteorological stations, those are providing real-time information. So we have question, is this sufficient for the disaster management or for early warning system? We have several questions of such types. So if you look at this research done by Pradhan et al. From government agency, he did research using 60,000 landslides and prepared a map. We can see several landslides are concentrated on the mid-hills of the Nepal, and that are prone to disasters. So if you look at the landslide susceptibility map, we can see those mid-hills are susceptible for landslides. So we need to think how we can design early warning system. That is the question for us. So if you look at this figure, I will try to summarize those. From this figure also, we can see, if you look at the central Himalayas or the Himalayas of South Asian Himalayas, we can see some geophysical settings, high mountain, mid-hill, and low-lying areas. In high Himalaya, we have glacial lake, snow-capped mountain. And if you look at the mid-hill, we have reservoirs, bridges, and those are river system, those are narrow. And if you look at the Tarai part, we can see the aggregate and degraded river system, wide river channel, and several agricultural land and those. If you look at the potential hazard in mountainous, high mountain area, we can see glacial lake outburst flood. In middle mountain, we can see the possibilities of landslide, which can create the landslide dam, and which will further push to the landslide dam outburst flood, and it will make disaster like in Melamchi river system. And if you look at the Tarai, there is possibilities of flood. That could be flash flood or fluvial flood. So we need to think about this. So we have various settings from high elevation to river valley. There is interaction between single disaster to multiple hazards. So we need to think about this. So from this figure, we can say that the cascading hazards are becoming more prevalent in the central Himalayas. Yes, we can think, we can look from those maps also. Primary hazards like earthquakes, avalanche, and landslides often trigger secondary hazards like gulf, landslide dam, debris flow, flooding. So compounding the risks to human settlement, infrastructure, and ecosystem, risk management strategies are commonly tailored to single hazards. We need to think about this. So if you look at the second figure, this figure shows the some kind of combination of disaster, mode of cascade, and their impact and duration of impact. If you look at this figure, for example, for Seti case, the triggering factor is the avalanche, and then the secondary hazards are landslide, debris flow, and flash flood, and its impact on human settlement, energy, transportation, and water supply, and duration is around weekly. Impact duration is around weekly. So, for example, if you look at the Melamchi, the triggering factor is landslide, and its secondary hazards are landslide dam, debris flow, dam breach flood, and its impact around yearly, and then it impacted to different sector, as I mentioned earlier, like human settlement, energy, transportation, trade, and those things. So I'm trying to conclude. So from those analysis, what we can see that the in central Himalayas and the South Asian Himalayas, we have complex geographical terrain, so need deeper studies on geology and geomorphology. So this kind of cascading hazards are more common in Nepal, so demanding a more holistic approach in hazard and risk management. We can see that from the previous figure also, cascading hazards leading to cascading disasters. So several studies had been done in those central Himalayas, even no clues about the glacial deposits in upstream of the Melamchi area before disaster. So we need to think about this. So I already mentioned due to the informal risk communication from upstream to downstream, significantly reduces the disaster. So we need to think about the community-based early warning system. So no mechanism to describe the cascading hazards in mountainous areas. Still, we need to think about the research. We don't have the process mechanism of those kind of cascading hazards. So we need to invest to better understand and better prepare. Integrated risk assessment is necessary. Based on those, we need to prepare the early warning system. And I will try to summarize some way forward from those review. We can see that the Nepal's Himalaya is prone to cascading multi-hazard, like in Melamchi, I already mentioned, complex to understand. So we need multiple hazard risk assessment, multi-hazard and multi-sectoral early warning system is required. For example, for flood, we need model-based estimation, flood forecasting, and early warning system. We need to think for flood. Similarly, for landslide, we are analyzing the based on Newtonian flow. We need to think about the sediment laden flow. We need to develop the landslide early warning system. In case of GLOB, we need to invest in dedicated remote sensing software, hardware, and human resources, and need to develop the GLOB early warning system. And I tried to summarize in 4 different subtopics. In second, I'll try to summarize in data information system. We need high density data network. We need to blend the in situ, that could be agency managed or citizen science-based data management, and the remotely sensed data set. We need to blend it. We need central database management system. We need to share it on time. We need to improve our existing knowledge and resources. We need to develop the impact-based forecasting. We need to increase the data collection and sharing. If we look at the implementation modality, we need to think about the localized hazard and susceptibility assessment. It should be in local language, so it would be easier to communicate. It would be easier to dispatch the information on time. We need to integrate the concept of citizen science and agency managed early warning system. We need quick analysis of information and delivery on time. We need to promote the citizen science to understand those disasters, and need to collaborate with the local palikas and local municipalities. We need to strengthen those. And we need the collaboration and cooperation, like we need collaborative body like High Mountain Research Center. We have transboundary impact from China, from Tibetan plate to India. So we need some kind of collaborative body to communication in such case. We need clarity and coordination in governance. So we need individual hazard specific working group. We need to have the collaboration between like NDRRMA, as mentioned earlier by Professor Dixit, and Anil Pokhrel CEO is also here, and Rajendra Sharma is also presenting. And then universities and different research organizations, we need to have collaboration. So I think I've just presented some experiences from LMC. So for the policies and governance sector, maybe Rajendra ji will explain more in detail about the government policies and other things. So thank you very much for your kind attention.
Thank you.
Thank you.
Thank you, Professor Thapa. So now we go over to you, Mr. Rajendra Sharma. Yes, you have got 15 minutes. Go ahead, please.
Hello.
Yes, loud and clear.
Yeah.
Loud and clear.
Can you see my slides?
Yes,
sir?
go for
Yeah.
PPT. Yes.
Okay.
Very good.
We can see this.
Thank you. Thank you. First of all, on behalf of National Disaster Risk Reduction and Management Authority, NDRRMA, I'd like to thank, and on behalf of Chief Executive Anil Pokhrel sir, I'd like to thank the organizers, especially Professor Mishra and Professor Dixit, for having us here in this talk program. This is Rajendra Sharma, working as a hydrologist in NDRRMA, Nepal. The title of my presentation is Multi-Hazard Early Warning System for Effective Disaster Management, Experience and Lesson Learned from Nepal. We all know that Nepal is a country with high risks from multiple hazards, as Dr. Thapa also mentioned before. Hazards like flood, landslide, lightning, earthquake, windstorm, forest fire, air pollution, etc. So we are at the risk of these hazards. Talking about early warning system, Sendai framework for disaster risk reduction has also highlighted about increasing the availability of multi-hazard early warning system to the people, to all the people by 2030. Similarly, disaster risk reduction strategic action plan of Nepal has also prioritized like development of multi-hazard early warning system for disaster preparedness. The figure in the bottom right corner shows the four pillars of early warning system. There are the 4 major pillars for the early warning system, namely risk knowledge, observation, monitoring and forecasting, communication and dissemination, response capability. So these all 4 pillars should be in intact position. It should be robust so that the whole system, whole early warning system can work better. So this slide shows the status of early warning system for various hazards in Nepal. Early warning system for flood is available, although we have to do a lot in flood also, but still some early warning system in flood is available in Nepal. And we are piloting for landslide early warning system. In few areas we are piloting, but it has not covered the whole Nepal yet. And for other hazards as shown here, like lightning, earthquake, windstorms, forest fires, we don't have early warning system. And currently NDRRMA is planning to make the system multi-hazard early warning system covering all these hazards. So let me give an example of flood monitoring and early warning system that is being used in Nepal. Currently, we are using this kind of system, and Nepal passed from various stages of flood early warning system. That is from WAS to 1. For example, in early days, in 90s, the people used to go up in the tower and look at the northern side, look at the river there, and if flood is coming, they just inform the people living in downstream. That was the very primitive type of early warning system used in those days. And after that, we used watch and warn system. That is by looking at the gauge stations and just informing the people downstream. That was in late 90s. That system was used, but currently we are using the automated type of system for monitoring and observation. We have automatic stations which measures the water levels and rainfall also, typical bucket type of automatic stations. Through that stations, now we are graduating the early warning system in flood. So this slide shows the communication system that is currently being used. We are using the SIM card for SMS dissemination and taking the data from the station to the central server. We are just using the SIM card, GSM phone sets. So this is not a perfect type of system, but we are graduating from this system to like a common alerting protocol, CAPS, and in high areas where there is no tower for this GSM telephone towers, we also use satellites phone irradium system. For example, in Bluff areas, in glacier lake outburst flood areas, we use satellite phone. Currently, we are giving the mass SMS to the communities. We have made some polygons, various polygons in flood affected areas, and if the level of water reaches warning or danger level in the stations in upper catchments, then we just inform the people living in the vulnerable areas of the lower catchments. This is how we are practicing now. But this is not enough. National Disaster Risk Reduction and Management is planning to do some national multi-hazard early warning system, which covers all the hazards, and we should give the information to the people through all the media. That is our concept. So this slide shows from for flood, drought, landslide, forest fire, each of these hazards, several institutions, they are mandated for the measurement, for the observation of these systems. For example, Department of Hydrology, Meteorology, Department of Forest and Soil Conservation, Department of Mines and Geology, Department of Water and Use, Department of Water, Irrigation, and also for pandemic, Health Emergency Operations System, centers, National Academy for Science and Technology. These all institutions are mandated for particular type of hazard, for the observation and monitoring of particular type of hazards. After getting the information from those, early warning information from those institutions, National Disaster Risk Reduction and Management Authority, we are trying to make one decision support system, common alerting protocol, to disseminate the information, early warning information to the people living in vulnerable areas. Not now we are just making one flat type of polygons and just giving information to each and every people living in that polygon. But we are planning to do impact forecasting. Which area or which population is more impacted by the given hazards? We are focusing on that, and we are trying to make a red zone, green zone, yellow zone, so that we can give the information and we can act accordingly. Like for early actions also, we can do accordingly. So that is our concept now. So as I mentioned before, the first part of early warning system, that should be the visualizing the risks. That is the first part that should be taken into consideration, and where to act is the main concern. And the answer will be given by the multi-criteria risk analysis and impact-based forecasting and warning. So communicating a complete disaster picture through information on exposure, hazard, vulnerability, and capacity and resources using a storytelling approach. Superimposition hazard maps with information on land cover and critical infrastructures to show the exposure of the elements to hazards, real-time quantification of potential impact level at the household level, plan activities for mitigation and preparedness. So these are the things that we are trying to do. NDRRMA is trying to do now in Nepal. So we are trying to map in household level. We are trying to get into the impact-based forecasting, not just telling all the people living in the Thapa area, oh, flood is coming. Not like that. We want to go to in the household level. So for that, visualizing risks is the first step. And after visualizing risks, communication is another vital area that we should work on. And common alerting protocol CAP, we are working with RIMES, Thailand, to establish CAP in Nepal. This CAP is a digital format for exchanging emergency alert to be disseminated simultaneously over multiple communication pathways, all hazard, all media. So for this system also, NDRRMA, National Disaster Risk Reduction and Management Authority, is working. So after this, if we can make the robust type of CAP system visualizing risks, observation monitoring, and then only we can do the early actions and response part. So people in action after getting this early warning, these are some figures. The people after getting the early warning, they are being shifted to the evacuation centers. So these are some figures. So strategy and action plan for multi-hazard early warning system. Policy and legal framework improvement, that is the vital part that we are working on. As per the decision of executive committee, which is chaired by Minister of Home Affairs, concept note and action plan for multi-hazard early warning system is being developed, and NDRRMA is developing that concept note and action plan for multi-hazard early warning system currently. And institutional structure and mechanism for mechanism strengthening is another action that we should work on. Plan to establish the sector section regarding early warning and early action in NDRRMA. So in NDRRMA, we are trying to make one small unit, small section who works solely in early warning and early action works. So research that we are doing and we have to improve. Still, we should collaborate with the research institutions, academia, which we are doing. Technology and infrastructure enhancements, coordination with various national and international organizations like JAXA, NASA. We are working for communication as well as for monitoring of rainfall, satellite monitoring of rainfall, and other technology transfers. Human resource management and capacity development, National Disaster Risk Reduction and Management Authority and Ministry of Home Affairs, we are trying to make organization survey for this human resource management, and in that organization and management survey we are planning to take, as I mentioned before, planning to make one section or division who works solely on early warning, early actions. So financial resources, monitoring, evaluation and learning, bilateral and regional cooperation strengthening, these are the other strategy and action plans that we are working on. So I think this is the end of my presentation. If there are any queries, I will try to address them. If I have missed something, my chief executive is also here. He will also help me. Thank you.
We'll now go to Dr. Pankaj Kumar. And Pankaj Kumar, I introduced earlier. Are you okay?
Yes, sir.
So now the floor is yours for presentation. Please.
Okay.
You have maximum 15 minutes.
Okay, sir.
Make your presentation within that. Okay.
Okay, sir. Thank you so much. Can you hear?
Yes.
Me?
Loud and
all
clear.
The participants. Can you hear me? And my PPT is visible?
Very much.
Visible?
Sorry? Yes, visible. Yes.
Okay. First of all, thank you, Professor Vijayanand Mishra, for providing this wonderful opportunity. Actually, I had various communications through mail with you, and I'm also thankful, Professor Mahua Mukherjee, for encouraging me to present myself in this Café talk. As we all are assembled here to talk about early warning system and South Asia disaster scenario. Actually, it means that how the early warning systems can mitigate disaster scenarios in South Asia. So with this regard, I will be talking about earthquake early warning system, which we have developed for Uttarakhand region in India. As we know that earthquakes are very deadly and they can destroy entire city in few seconds. So the reliable, as of now, we know that reliable prediction of earthquakes are not possible. So earthquake early warning systems are basically used for alerting people. And the alerts are issued few tens of seconds before the arrival of damaging waves. The earthquakes early warning system have been developed for various parts of the world, starting from Japan, Korea, Taiwan in the east to the United States, Mexico in the west. As we know that 59% of the land area of India is seismically hazard. So we have to develop an early warning system for the seismically active regions of the India. As various great earthquake has occurred in the past in the Himalayan region. In 1905, Kangra earthquake, magnitude was 7.8. Again in 1934, Bihar Nepal earthquake, and 1897 Assam earthquake, and Assam Tibet earthquake. The various seismic study has been carried out, and it has been found that there is central seismic gap between Kangra epicenter of the Kangra earthquake and Bihar Nepal earthquake. Great earthquakes are already various large earthquakes are already overdue in this region. As we know that the primary waves travel faster than the secondary waves, so basically early warning system take the advantage of the difference of the speed of these two waves. In case of the on-site early warning system, sensors are installed at the same places where warning has to be issued. So the warning is issued based on the single sensors or the group of sensors in the close proximity. But the chances of false or missed alarms are high in case of the on-site warning system. This is the map of the regional early warning system. In case of the regional early warning system, sensors are installed in the seismogenic active regions, and the warning is issued at least the 4 sensors. 4 sensors records, and the chances of the false and missed alarms are very less in case of the regional early warning system. This is the architecture of earthquake early warning system. Sensors are installed in the seismogenic regions. They are connected through the dedicated network of the, as of now, we are using virtual private network over broadband of BSNL and SWAN network connectivity of the states, and the data is transferred to the central server, which we have set up in Earthquake Early Warning Laboratory in Center of Excellence in Disaster Mitigation and Management, IIT Roorkee itself. So data is fetched at the central server. Whenever earthquake triggers in the region, the early warning reports are generated at the server, and this message is transferred to the warning server. Then warning server disseminate early warning through the various mode. Like as of now, we are using siren and mobile application, and radio and SMS can also be used. This triangle represents the location of the sensors which we have installed in the Garhwal region and are connected through the BSNL connectivity. This picture is how we have instrumented the sensor in the region, and this map this figure shows the configuration during the installation of the site. As of now, in the Garhwal region, we have 50 stations connected through the BSNL. And now the triangles shown with the blue color represents location of the sensors connected through the SWAN network. These triangle represent the location of the sensors installed in the Garhwal region and are connected through the BSNL network. And this triangle represents the location of the sensors installed in the Kumaon region and connected through this one network. So as of now, we have around 106 67 sensors installed. This is the whole setup of earthquake early warning lab. Actually, the data is being fetched through the lease line and lease line at the computer center or in the IIT Roorkee, and from the computer center to the lab, which is present in the CoEDMM. For this whole setup, we have lease line switch, router network switches, server, and the monitor to display the continuous data waveform, and maintenance and operation in the lab. In-house, we have fabricated sirens, which we have installed in the field, and sensor box. We have developed sensor monitoring software, siren monitoring software, and the intensity map, which are basically required for the disaster management authorities to carry out aftermath operations. This map represent this figure shows the how the data from the sensors to the server is streamed. These streaming just showing the response of the sensor itself. Technical aspect of on-site and regional early warning system. In this accelerogram, you can see the P phase and S phases. Here in the below figure, you can see the 4 accelerodrums, and these rectangle represents the 3-second time window from the P onset of the earthquake. As soon as when server finds that the P onset has been triggered at least 4 stations, then magnitude is estimated, and if estimated magnitude is greater than 5, then warning is issued to the public. Actually, there was an earthquake and it was recorded by our server. In this figure, you can see there are 2 accelegrams. In this accelerogram, P onset and S onsets are shown here, and in this accelerogram, this P onset and S onsets are shown. The above accelerogram was recorded by the sensor, which was only 12 kilometers away from the epicenter, and below accelerogram was recorded by a sensor BHLS site that was 180 kilometers away from the epicenter region. So this picture represents if we have the regional warning system, then we can issue the warning here. But in case of if we have regional, we have on-site warning system, then we can issue the warning at this point. So if having regional early warning system, we can have this much more lead time to inform the people. There are various algorithms and parameters which are used in early warning systems, as cumulative absolute velocity, bracketed cumulative absolute velocity, and characteristic and predominant based parameters. As of now, we are using low pass filter peak displacement based parameter for the early warning. This picture represents the how a regional earthquake early warning system works. Here, this is the national emblem, and it represents the national capital Delhi. This represents the state emblem, and it is showing the location of Dehradun. Suppose we have the sensors are installed in the Uttarakhand region, and if earthquake occurs in this region, then it will be recorded by these sensors. This sensor, first of all, this hut represents the user site. I considered it Roorkee. These triangle which are popping up are showing that P onset has occurred at these stations, and central server is processing, and now the report has been created. This represents the epicenter, and red circle is showing the speed of the S wave, that is the damaging wave, and green showing the speed of primary wave. Here timer is shown the lead time for the Roorkee city. So now Roorkee has the 21-second lead time, 19 seconds, 18 seconds, 17 seconds, like that. How this video actually shows how an early warning system works. Now the people has only 3 seconds to shape themselves to take precautionary measures. 0 shows that secondary waves has occurred at your place. As of now, we have two mode to disseminate warning to the public: siren or routers, or the mobile application. Sirens have been installed in the district emergency operation centers present in the all 13 districts of Uttarakhand, and 51 locations in Dehradun and 15 locations in Haldwani. These sirens are installed in the government-owned buildings, school, colleges, hospitals, police stations, etc. Uttarakhand Bhukamp Alert app is indigenously developed by the Earthquake Early Warning Lab. This represents a screenshot of the app, and whenever earthquake occurs and warning is issued to the public, it shows the information about the tentative magnitude and the origin of the earthquake and the lead time. Here you can see the timer with the time. Here in this screenshot, you can see there is one important button, which is SOS button, and it is written in Hindi. Mujhe madad chahiye. Whenever an earthquake, suppose an earthquake has occurred and user has stuck in somewhere and he needs some help, so he can press this button, and the location of that user will be sent to the server of Disaster Management Authority, so that Disaster Management Authority can initiate search and rescue operations very fast. These are the Q codes for Android and iPhone mobile users. This app was launched on 4th of August 2021. Yes, sir.
Okay.
Yeah, please continue.
Yes, and this.
2 minutes. 2 minutes, please. 2 minutes.
Okay, sir. This app was launched on 4th of August 2021, and we had a media coverage, and it was reported in the international papers as well as the local newspapers. Our team goes to the go to the field and create awareness among the mass to install the mobile application. This is the pamphlet which we have developed to create this pamphlet is created to create awareness among the masses for the student when they are in the classrooms, and for the student when they are in hostels, what they should follow during the earthquake and what they should not. We conduct the mock drill on every first day of every month at 12 noon. This is you may hear the sound. You may hear the sound that this kind of voice is used to create awareness. Estimated lead time can be estimated. This is the average and minimum maximum lead time for the few important cities of Uttarakhand region. As of now, 12 minor earthquake has minor and light earthquake has occurred in the Uttarakhand region, and 12 for these 12 earthquakes we have successfully issued alerts to the public. This is a success story. On September 11, 2021, a magnitude of 4.7 triggered in Chamoli region. The alert was issued to the public, and this is the lead time for the Dehradun, Haridwar, and like these cities. And for Dehradun, it was 14.6 seconds. And for Delhi, it was 15.8 seconds. So this was the lead time. If it would be an earthquake of larger magnitude, then people can save their life and property. This early warning system is the first. Uttarakhand early warning system is the first earthquake early warning system in India, and we have also developed first early warning mobile applications. And this is the world first early warning app that can send the location information of the users stuck during earthquake to the disaster management authorities for rescue purpose. Actually, it is my privilege that Dr. Kamal, PI of the project, encouraged me to present this work in this cafe talk. I am also thankful Professor ML Sharma, Professor R.S. Ekka, Professor Pratibha, and our technical staff for supporting in establishing the early warning system. Thank you so much.
Thank you. Thank you. Thank you. Thank you very much, Dr. Pankaj.
Yes.
And okay. Now we should go to the fourth presenter, and is Mr. Srikrishnan Siva Subramanian. He is also. Are you there? Okay. Please, this is your floor, please. And
thank you, Professor Mishra.
Try to complete within 15 minutes.
Sure,
Okay?
sure.
Thank you.
Yeah. Is my screen visible to you?
Yes, please.
Thank you. So thank you, Professor Mishra and IDRiM for giving me this opportunity. Myself, Dr. Srikrishnan, I am an assistant professor at the Center of Excellence in Disaster Mitigation and Management, IIT Roorkee. And I have been listening to the previous talks by Dr. Thapa and also by Dr. Rajendra Sharma and Dr. Pankaj. All of these are like territorial scale early warning system. So I will be glad also presenting our contribution to a territorial scale early warning system for landslides in India. Without taking more time, let me go with the presentation. And Professor Mishra has kindly given us some guideline or agenda, like how we can cover this presentation. And he also cautioned that it should be an informal way. Also, some technical aspects are here. So hope you will not mind about that. I will try my best to touch upon these agenda topics, which is suggested by IDRiM. So this we all know why it is important to have a landslide early warning system as a tool in DRR, especially for regions in the Himalayas, especially for us in the Uttarakhand Himalayas. The most common landslide that happens is the debris flows, debris slides, which is of also like shallow landslide nature and also like rainfall induced debris flow in nature. Since the mechanism of the debris slides and debris flows are itself complex and there is much of the physics need to be understood, establishing an effective early warning system for these kind of geohazards is very complex. So with the increase of extreme events, which is possibly caused by climate change, it is also cautioned by experts that there will be robust increase in rainfall in the future. So there is an urgent need for landslide disaster mitigation methods to be employed in the Himalayas for the welfare of human life. If we look at the scientific rationale of landslide early warning system, that these are the countries, what you can see in the presentation, if you show my pointer. So many of these countries use, in a territorial scale landslide early warning system, many of these countries use intensity duration threshold for rainfall induced landslide based on rainfall intensity and duration. There are also countries which use a complex based threshold. Most importantly, that comes to play is Japan. Japan uses a soil water index based complex threshold to catch the index property of rainfall as well as like soil moisture. That system is being governed by MLIT and also Japan Meteorological Agency in Japan. During my time in Hokkaido University, Japan, I had an opportunity to work in the real-time landslide early warning system. And at that time, we extended the applicability of the soil water index-based Japanese early warning system to also for snowmelt-induced landslide. Now, in India, what we are trying to do as being in IIT Roorkee is, as you can see here, number 6, there is an experimental landslide early warning system for rainfall-induced landslide in India that is being only operated experimentally, okay, not in operation. So it is a prototype and it is being handled by the Indian Space Research Organization, mainly by their National Remote Sensing Center in Hyderabad. Apart from this, we do not have a landslide early warning system working at the territorial scale in India. That is the present scenario. Having this background, if we look at from where we can learn to implement landslide early warning system in India, of course, we have to learn from countries which have developed these systems already. One such country is Japan, as I also mentioned earlier. So in Japan, during my time in Japan, we have worked on developing some numerical models which understands the mechanism of landslides in a more proper way, and then can quickly tell you where and when a landslide will occur. So these are some contributions which includes the soil water index based systems. And right now, what we are trying to do in IIT Roorkee is we are trying to implement the soil water index based early warning system into territorial scale landslide early warning systems in India. So we have developed like 2 numerical models, which is also quickly functioning numerical models based on lumped hydrology and geomechanics. And this is not real time as of now. This is being in a prototype, but this can tell you where and when a landslide will occur, mainly for debris slides, shallow landslides, and debris. For this, we have developed a methodology, and this system we are currently trying to implement for the Uttarakhand state, as you can see here. So these are the surveyed locations of landslide, and using this surveyed location of landslide and inventory, we are trying to build our own numerical models and implement it in a territorial scale system, then kind of trying to provide early warning. But the project is just started, and we are just focusing on like collecting the inventory and other things. But what we think is implementing an early warning system to a new geological area is not that simple. So there need to be a lot of geotechnical and geomechanical studies to be done to know the characteristics of the mass that is failing. So that's where we come into play. We do these kind of numerical modeling studies as well as experimental based studies in IIT Roorkee. Then we kind of improve the early warning system. So this is our experience from Hokkaido, Japan, where we improved the predictive capacity of the Japanese early warning system. The Japanese early warning system earlier did not account for snowmelt into its component to calculate the soil water index. What we did is we also incorporated the snowmelt, and we incorporated it in every 5 kilometer grid. That is already there, 5 kilometer grid. What we additionally did is we introduced snowmelt to these curves, and then it also became applicable for snowmelt induced landslide. But for India, if you want to incorporate the soil water index system, you need an existing experimental framework, which is, even though it is not in real time, at least a prototype. So we approached NRSC, ISRO. They are having an experimental early warning system for selected road corridors in Uttarakhand. But that system doesn't use a complex threshold, whereas that system uses an intensity duration threshold. But we also have our numerical model, which can improve the predictive capacity of this intensity duration threshold based landslide early warning system as well. Because our numerical model is bit physics based, it is not based on statistics, and it can improve the predictive capacity of landslide based on the studies what we are doing. So this is an overview of the road corridors within Uttarakhand. It is mainly implemented along the Char Dham area in Uttarakhand. Now we are working on improving the predictive capacity of the existing system, And once this is being done, then we will introduce the soil water index-based early warning to the existing system. What is the biggest challenge is implementing territorial scale landslide early warning system to a new geological setting is not easy, because we have very limited historical events of precipitation records to calculate the threshold. So we need an additional method that can capture the threshold for future extreme events. So alternatively, the only way what we could see to go is numerically simulate the occurrence of landslide using various magnitude of precipitation and inform us about the landslide triggering condition. For this purpose, the numerical models what we developed recently in Japan as well as here in IIT Roorkee will help. So this satisfies the invitation of the improvement and advances to the existing territorial scale landslide early warning system. But I should be very honest here, this is just a beginning and there is a long way to go. So what we believe now and the points to ponder is, we all know that how important it is to mitigate landslide disaster in Uttarakhand Himalayas. Extreme events are continuously happening. So we believe that the proposed new early warning system that we are working on with the revised intensity duration threshold will improve the predictive capacity of the existing system. And this has to be done with the proper rainfall forecast as well. So we are actually depending on the good rainfall forecast that we are collecting from the India Meteorological Department. So I come to the final point of this slide. So there is an article by a journalist, Flavia Lopez, but this has been surveyed from various people who are actively working on early warning systems in India. As you can see here, India needs an urgent early warning system for landslide, but challenges above. The present situation is, of course, India is developing an early warning system for landslide, but the title itself tells us that it is not likely to be operational before 2025. So 2025 is not that far, but we are making effort. But what lags also mentioned in this article is the coherent effect. Means many of the organizations are working independently and they are putting their efforts, but a holistic efforts is not coming. That's why there is much time. So with this, I conclude my talk, and I also thank my previous presenters to also account for, like Dr. Rajendra Sharma mentioned, that the landslide early warning system, what Nepal is doing, it is also in a pilot phase. It is the same in India as well. So we have to learn mutually, and also for institutions in India, we have to work holistically to come up with the operational landslide early warning system. If not holistically, then we will be delayed even after 2024. With this, I thank you all for this excellent opportunity. I am open for any questions and discussions. Thank you, Professor Mishra.